Hi, welcome to another video of differential equations. So today we're going to be doing exact method of solving differential equations. So let's get started. Well, first thing we have to know about exact differential equations is that it has to be a certain format, right? So I'm going to give you the format really quickly. And there's going to be a couple symbols that maybe you've never seen before. And I'm going to go over what those symbols mean. Okay? Okay, so if you've never seen this before, this is the partial derivative of f with respect to the partial derivative of x. And this is a partial derivative of f with respect to the partial of y. Okay, and if you don't know how to take a partial derivative, I could show you really quickly. So we're always going to have a function, f of x, y. And that's going to represent our function. So let's just say this is x cubed times y plus okay, so this is our function. And then we're going to take a partial derivative of f with respect to x. So we're going to take our function, and we're going to take, we're basically going to do the derivative of each x, but with only respect to the x. Anything else will be a constant. So let's do this one. So if we take the derivative of x, that's going to be 3x squared y. And like I said, the y is going to be the constant, so it's going to stay the same. However, with this y, it's by itself. It's not being multiplied. So it's by itself. So that's going to be a 0. Just like taking a derivative of any constant, it's going to be a 0, right? I'm just going to leave the 0 there so you know where that came from. Take the derivative of that. It's going to be 2x. And then take the derivative of x right here. It's going to be simply y, because that x, the derivative of that x is 1, but we never represent that. So this is how you take the partial derivative of f with respect to the partial of x. So let's take a partial derivative of f with respect to the partial of y. Well, we're going to do the same thing to this function, except with respect to this y variable. So that means that if we take the derivative of this, that's going to be x cubed. Take the derivative of that, that's going to be 1, because now it's with respect to y. Plus, well, if we take the partial of this y, well, this is now the constant. The x is now the constant, so that becomes a 0. Okay? So now if we take the derivative of y here, that's just going to leave the x. So this is how you take the partial derivatives with respect to whatever variable. Okay, so you'll see the partial derivatives indicated by these, the small variable down there. Or you'll also see like this. This might be more intimidating if you ever saw it, but they mean the same thing. The partial derivative of f with respect to the partial of x. Okay? So before we get into it, just wanted to give you some background knowledge on what the partial derivative was. All right, so with that knowledge, we're going to go ahead and continue. So great, you guys are now masters at partial derivatives. Okay. Well, if we think back to our homogeneous method of solving differential equations, we are basically looking at the same format. So this was for the homogeneous, and now these are going to be partly related. Okay. So now I just want to point to this fact. We're going to be using this a lot, where the partial of f with respect to the partial of x, so f little x, whatever you want to call it, is equal to m. Okay? And this partial of f with respect to the partial of y, that's going to be equal to n. All right? And since these are derivatives, if we were to take an integral, we're going to get what our previous function was. So if I take an integral of this partial of f with respect to the partial of y, and I take the integral of both sides, I'm going to get this little f is equal to, this is with respect to dx, okay? So I'm going to get the integral of m dx plus h of y. Now, where does this come from? Well, going back to what the partial derivative was, is that there had to be some kind of a y variable where it was a constant. And when we take the partial of this with respect to x, we're simply going to get this, and this is equal to 0. Right? So if we take the integral, we're going backwards. We're reversing the partial derivative. Therefore, we have to have our y variable, whatever it was, still in there. Okay? So if we take our partial of f with respect to the partial of y, we're going to get that equal to n, right? So if I were to take the integral of that as well, I'm going to get this little f is equal to, that was with respect to dy. Okay, so I'm going to get the integral of n dy plus g of x. And that goes back to the idea again where we had to have an x variable somewhere, whatever x variable that was, it had to be in there. Now this is a constant basically. So if we were to take the partial with respect to y of this equation, we're going to get this. Because now this is a constant and it just goes to 0, right? And then if we take an integral of 0, well, that's just going to be a constant. Okay? So that's important to see. Okay, so with that knowledge, I think we can start with one of our problems. So if you're following along in the book, we're going to do number 2 for 2.4. Okay, and we want to check for exact for this equation. 2x plus y dx minus x plus 6y dy is equal to 0. Okay, so like most of the cases, you want to check to see if it is what it is. So for this case, we want to check to see if it's exact. Okay? Now for something to be exact, for an equation to be exact, its partial derivatives have to be equal to each other. Okay? This statement has to be true in order for something to be exact. If this is true, therefore our differential equation is exact. Okay? Hopefully that makes sense. And like I said, the other way of noting this was simply our little notation there, right? Okay, so that is our goal when we're checking for exact. All right? Okay, so let's go ahead and take a look at this one. So the first thing I'm going to do is I'm just going to distribute that negative because that does apply to both of them. So that's just going to be 2x plus y dx minus x minus 6y dy. Okay? Well, if we look at this equation, this is a format basically. This is our m. And this is our n. N is usually paired up with a dy. M is usually paired up with a dx, as we see here. Okay, so what do we do now? Well, my partial of m with respect to the partial of y basically the same thing, right? So this is my m right here. So now I'm going to take a partial derivative with respect to the only the y variables, right? So this is going to be a 0 because this is a constant. And this is going to be 1, right? So the derivative of y is simply 1. And then if I were to take my partial derivative of n with respect to the partial of x, so all the x variables are going to have the derivative, and then the y's, well, they're constant, so they're going to be 0. So if I take the derivative of negative x, I'm just going to get negative 1. And this becomes a 0 because y is a constant. Okay, so if we could see now, well, these two partials are definitely not equal. So therefore, to answer this question right here, this differential equation is not exact. It's not exact because the partials aren't equal to each other. Okay? So that's pretty simple. Let's go ahead and do another problem. So now that we have an understanding of how to check for exact, it's going to be the same thing for all of them. If you're going to check for exact or not, when the partials are equal to each other, it's going to be exact. You answer the question. Boom. So now let's actually solve these equations. Okay? So I have this. So I have 3x squared times y plus ey quantity times dx plus x cubed plus x e to the y power minus 2y dy equal to 0. Okay, now what in the world do we do now? Well, like I said before, usually our m is paired up with our dx. So that's what I would usually look at first, is where's my m and where's my n, right? Okay, so I definitely want to check to see if they're exact, because if they're not exact, then I can't use the exact method to solve it, okay? So let's take our partials. We're going to take the partial of y of this. So if I see here, I'm going to have a 3x squared. Here I have ey still, e to the y power. And then I'm going to take my partial of x here. So I'm going to get equal to 3x squared. That x goes to 1, so I'm going to get e to the y power. And if you see here, both my partials are equal to each other. Therefore, it is exact. Therefore, we can continue. Great. So we're going to use the fact that m was equal to f x. So if our m is equal to the f partial of x, well, this is my m, so I'm going to write that down. 3x squared times y plus e to the y power. Okay, great. Now what I'm going to do is I'm going to try to find that little f. So how do I change this partial derivative into a little f, the f by itself? Well, I'm just going to take an integral of both of those. So now I'm going to get my f all by itself. Okay, so this is going to be x cubed y. We don't do anything to the y because it's a constant. Plus this x e to the y. And like we said before, we need to have that y variable. So it's hy. All right, so now what we're going to do with this little f, we're going to take a partial of y from this f. Okay? So now that's going to become x cubed plus xey plus h prime y, because that's the derivative of this constant. Whatever the constant is, it's now the derivative of that. All right, great. So now we're going to use another idea where if we look here, we use the fact that n is equal to f of y. Okay, so, well, this is the partial of f with respect to the partial of y. Well, that means that this is equal to n, right? Well, what was our n? That was our n. Okay? So what we're going to do is we're just going to bring this guy up. So that was x cubed plus xey plus h prime of y equal to n However, we're going to input our n, which was this here, equal to x cubed plus x e to the y power minus 2y. Okay, so now if we see here, I'm going to have stuff being able to cancel out. I'm just going to do this all in one step. Now I have h prime y equal to whatever's left over, which was our negative 2y, right? Okay, so now I'm going to take, an integral because that's going to give me hy. And if we look here, this is our constant, hy, which is an unknown. So basically what we're going to do is find it, right? So I'm going to take an integral of this h prime y and the integral of this negative 2y. And this is now going to give me my h of y, my constant that I found there. Okay, and that is going to be negative y squared. Perfect, we found that hy. Well, what does that mean? Well, that means we're going to take this equation, this little f, because that's the one that has this unknown constant. Well, now we're just going to plug in the now known constant, right? So we have x cubed times y plus x e to the y power minus y squared. And this is going to be equal to c. All right. So that's basically the process of using the exact method to solve a differential equation. And the interesting part about this method is that this is similar to a multivariable calculus computation when you're solving for conservative vector fields. When you're solving to test to see if the vector field is conservative or not, you might do one of these. Let's do something similar to that, right? Okay, so let's move on. Okay, so let's find another juicy problem. Okay, so there's also something called integration factor. Perfect. Okay, so integration factor the integration factor is basically, what we're going to see here is that the integration factor is going to help us turn a not exact differential equation into an exact differential equation. So instead of just simply giving up when our equation is not exact, we're going to change it into exact. So let me show you what I'm talking about. Okay, so we have negative y squared dx plus x squared plus x dy equal to 0. And then our integration factor is usually indicated by this mu equal to, so mu x of f That's going to be equal to 1 over x squared y. Okay. So let's figure out if this equation is exact or not. So this is my m, this is my n, and like I said, it was usually paired up with the dx, and is usually paired up with dy. So if I take my partial derivative of m with respect to the partial of y, I'm going to get negative 2y. And if I take my partial of n with respect to the partial of x, I get 2x plus y. Well, that certainly doesn't look equal, right? So we could say that this isn't exact. Not exact. So what we're going to use is our integration factor. And we're going to multiply this to the beginning equation. So you're going to multiply the integration factor to the original equation. Great. So now we have negative 1 over negative y over x squared dx plus we have a 1 plus 1 over x. Okay. Or did I do that incorrectly? Well, according to my notes, I did. We have the x plus y, okay, over xy. And looks like I did it correctly, but I did another way. Okay, so we have that. And now if we were to take the partial derivatives of these, well, since this is our new m, this is our new n, we're going to get that my is equal to negative 1 over x squared. And if we take our partial of n with respect to the partial of x, well, we are going to get xy minus xy minus y squared over xy squared. Okay. And now we could see here that these would cancel out. And then this power of 2 could be moved inside. And now we have x squared times y squared. Well, now we're going to have that equal to negative 1 over x squared, because these would cancel out. So great. Now our partial derivatives are equal to each other. Now we can continue to solve it. Wonderful. So now we have, with the fact that, using the fact that m is equal to the partial of f with respect to the partial of x, so we have f of x is equal to this new equation, because this is the exact equation. This is the exact equation. Excuse me. And this is our not exact equation. So we're going to use this one. I'm going to put a heart around it because we love this one. So we're going to use this one. So f of x is equal to our m, which is negative y over x squared. Okay. That's with respect to dx. And if we take our integral of both sides, we're going to get that f is equal to y over x plus hy. So now we have our constant. Okay, great. So now what we're going to do is take a partial derivative with respect to our little f with respect to y, right? Okay, I'm just going to go over here. I need some room. So we're going to take this. F is equal to y over x plus hy. Now we're going to take a partial derivative with respect to y, and that's going to equal one over x, sorry, plus h prime y. This is a prime. Okay. And so if we go back to the fact that f of y is equal to n, we can set this equal to n, and our n from our new equation, from our exact, the one that we love, if we take our n from there, we have this equal to x plus y over xy. And now it would be a good idea to split this up because now I can cancel this out, these x's and those y's, and I'm left with 1 over y plus 1 over x. And you'll see why I did that, because now I could subtract my 1 over x here to both sides.